the birth of the universe, the Big Bang. Imagine this: 13.8 billion years ago, everything, every star, planet, and particle, existed in a point smaller than an atom. Then, in an instant, the universe exploded into existence. Not an explosion like fireworks in the sky, but a rapid expansion of space itself. This was the Big Bang. It wasn't just the birth of matter, it was the beginning of time and space itself. How do we know this? Well, let's start with the cosmic microwave background, or CMB. It's this faint glow of energy left over from the Big Bang, spread across the universe like an ancient fingerprint. Discovered in 1964, it's one of the strongest pieces of evidence we have. And then there's the redshift of galaxies, Edwin Hubble's discovery that galaxies are speeding away from us, showing the universe is still expanding. Now, imagine the first moments of creation. In the blink of an eye, the universe went through something called inflation, expanding faster than the speed of light. Energy cooled, and the first tiny particles of matter started to form. Quarks combined into protons and neutrons, laying the groundwork for the atoms we're made of today. But here's the kicker: we still don't know what caused the Big Bang or what existed before it. That's one of the greatest mysteries of our time. Formation of the first atoms and stars. As the universe cooled to about 3000 degrees Kelvin, a far cry from the unimaginable heat of the Big Bang, something magical happened. Protons and electrons combined to form the first atoms. Mostly hydrogen and helium. This was the universe's first breath. But then came along, dark silence, known as the cosmic dark ages. For millions of years, there were no stars, no galaxies, just a sea of invisible hydrogen gas. Then, gravity started doing its thing. Clumps of hydrogen gas grew denser and hotter until they ignited in nuclear fusion. This was the birth of the first stars, called population 3 stars. Now, these stars weren't like the ones we see today. They were massive, bright, and short-lived. They didn't contain heavier elements like carbon or oxygen, because those elements hadn't been created yet. But when these stars died in spectacular supernova explosions, they forged those elements and scattered them into space, seeding the universe with the building blocks for life: galaxies, islands of stars. Let's zoom out for a moment and talk about galaxies, those colossal islands of stars scattered across the cosmos. Each galaxy contains billions of stars, along with planets, gas, dust, and, intriguingly, dark matter. Our own galaxy, the Milky Way, is just one of about 2 trillion galaxies in the observable universe. Galaxies come in all shapes and sizes. Spiral galaxies, like our Milky Way, have elegant arms swirling around a bright core. Elliptical galaxies, on the other hand, are more like footballs, less flashy, older, and quieter. And then there are irregular galaxies, which don't play by the rules and have no defined shape. Often, their chaotic appearance is the result of collisions with other galaxies. But how did these giants form? It all started with small clumps of matter in the early universe. Over billions of years, these clumps merged, pulled together by the mysterious force of dark matter. This invisible substance makes up about 27% of the universe and acts as the scaffolding for galaxies to form and grow. The scale of the universe. Let's take a moment to appreciate just how vast the universe is. Light, traveling at 300,000 kilometers per second, takes 8 minutes to reach us from the Sun. That's pretty quick, right? But our Milky Way galaxy is 100,000 light-years across. And the observable universe? That stretches for 93 billion light-years. To make sense of these distances, astronomers use light-years, the distance light travels in 1 year. It's about 9.46 trillion kilometers. And yet, even light-years can't fully capture the immensity of the cosmos. Here's something to blow your mind: the universe isn't just big, it's growing. Space itself is expanding, stretching galaxies farther and farther apart. This expansion is driven by something we call dark energy, a mysterious force that makes up about 68% of the universe. What's beyond the observable universe? We don't know, and that's what makes it so thrilling. Black holes, cosmic monsters. Now let's talk about black holes, the cosmic monsters that defy our understanding of physics. A black hole forms when a massive star dies and collapses under its own gravity. The result is a region of space where gravity is so intense that not even light can escape. There are different types of black holes. Stellar black holes are the remnants of dead stars. Supermassive black holes, millions or billions of times more massive than the Sun, sit at the centers of galaxies, including our own Milky Way. Then there's the hypothetical primordial black holes, which may have formed in the early universe. What makes black holes so fascinating is the event horizon, the point of no return. Once something crosses this boundary, it's gone forever. At the center lies the singularity, a point of infinite density where the laws of physics as we know them break down. But black holes aren't just cosmic vacuum cleaners, they can also power some of the brightest phenomena in the universe, like quasars. The life cycle of stars. Stars, those glittering jewels in the night sky, live dramatic lives. But did you know that every star you see is in some stage of a life cycle? Stars are born, they shine, and then they die. But the way they die depends entirely on their mass. Let's start at the beginning. Every star begins in a vast cloud of gas and dust called a nebula. Imagine this as a cosmic nursery. Gravity pulls the gas and dust together, heating it up until it forms a protostar. Think of this as a star in its toddler phase. As the core temperature rises to millions of degrees, nuclear fusion ignites. That's when the real magic begins. During its main sequence phase, where it spends most of its life, a star fuses hydrogen into helium. This process releases the energy that makes the star shine. Our Sun, for example, has been in its main sequence for about 4.6 billion years and has enough fuel to keep shining for another 5 billion years. But what happens when a star runs out of fuel? If it's a smaller star, like the Sun, it expands into a red giant, shedding its outer layers to form a beautiful planetary nebula. The core that's left behind becomes a white dwarf, a dense, glowing ember about the size of Earth. For massive stars, the story is much more explosive, literally. These stars end their lives in supernovae, some of the most powerful explosions in the universe. The core might collapse into a neutron star, an object so dense that a sugar cube's worth of its material would weigh billions of tons. Or, if the star is massive enough, it could form a black hole. The cycle of a star doesn't just end with its death, it seeds the universe with heavier elements, like carbon and oxygen, which are essential for life. The Milky Way, our galactic home. Now let's talk about where we live, not Earth, but our galactic home, the Milky Way. Imagine looking down on the galaxy from above. What you'd see is a magnificent spiral with long, curving arms radiating out from a dense, glowing core. Each of those spiral arms is packed with stars, gas, and dust. And we're in one of those arms, the Orion Arm, about 27,000 light-years from the center. Our galaxy is enormous, over 100,000 light-years across. If you could travel at the speed of light, it would still take you 100,000 years to cross it. And the Milky Way isn't just made of stars. It's surrounded by a halo of dark matter, an invisible substance that doesn't emit light or energy but exerts a gravitational pull, holding the galaxy together. At the heart of the Milky Way lies something extraordinary, a supermassive black hole called Sagittarius A. It's about 4 million times the mass of the Sun. But don't worry, we're far enough away to be safe. The Milky Way is also part of a larger neighborhood called the Local Group, which includes the Andromeda Galaxy. Fun fact, in about 4.5 billion years, the Milky Way and Andromeda will collide. But don't panic, by then, the Sun will be nearing the end of its life, and the collision will take billions of years to complete. So, if anything, it's something to look forward to in the far, Far future. The Solar System, a cosmic family. Let's zoom in from the galaxy to our own little corner of the universe, the Solar System. At the center is the Sun, a modest star that provides the energy for life on Earth. Surrounding it are 8 planets, each unique, along with moons, asteroids, comets, and dwarf planets like Pluto. Together, they form a cosmic family. The Solar System formed about 4.6 billion years ago from a cloud of gas and dust. Gravity pulled the material together, creating the Sun at the center. The leftover material flattened into a spinning disk, where planets began to form. The closer you get to the Sun, the more rocky and solid the planets are, like Mercury, Venus, Earth, and Mars. Farther out, you find the gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune. But the Solar System doesn't stop with the planets. Beyond Neptune lies the Kuiper belt, a region filled with icy bodies, including Pluto. Even farther out is the Oort cloud, a spherical shell of icy objects that marks the outermost boundary of the Sun's gravitational influence. Every planet and moon tells a unique story. For instance, Europa, one of Jupiter's moons, might have a subsurface ocean beneath its icy crust, an exciting place to look for signs of life. And then there's Titan, Saturn's largest moon, which has rivers and lakes of liquid methane. The Solar System is more than just home, it's a treasure trove of wonders waiting to be explored. Earth, the blue planet. Let's take a closer look at Earth, the only planet we know of that harbors life. What makes Earth so special? First, there's water. About 71% of the planet's surface is covered in liquid water, and water is essential for life as we know it. Second, Earth has a breathable atmosphere, a mix of nitrogen, oxygen, and trace gases. This atmosphere not only provides air to breathe but also protects us from harmful radiation and meteoroids. Earth's journey began 4.5 billion years ago when it formed from the same disk of gas and dust as the Sun. Over time, it differentiated into layers: the crust, mantle, and core. The core generates a magnetic field that shields us from solar winds, while the tectonic plates on the crust drive processes like earthquakes and mountain formation. But what truly sets Earth apart is its biosphere, the network of life that covers the planet. Life here began in the oceans about 3.8 billion years ago and has evolved into a dazzling variety of forms, from microorganisms to humans. Earth's relationship with the Sun is also finely tuned. We're in the so-called Goldilocks zone, where temperatures are just right for liquid water. The Moon plays a vital role too, stabilizing Earth's tilt and driving the tides. Every aspect of Earth seems perfectly calibrated for life. Coincidence? Or something more profound? That's a question worth pondering. The Moon, our celestial companion. Let's look up to the night sky and appreciate the Moon, our closest celestial neighbor and constant companion. The Moon is more than just a pretty sight, it's a key player in Earth's story. Without it, life as we know it might not exist. The Moon likely formed about 4.5 billion years ago from a colossal collision between Earth and a Mars-sized object called Theia. The debris from that impact coalesced to form the Moon. Over time, it has stabilized Earth's tilt, giving us consistent seasons and shaping our biological rhythms. But the Moon isn't static. It's slowly drifting away from Earth, about 3.8 centimeters per year. In the distant future, this will affect the tides and lengthen Earth's days. The Moon's surface tells a story of violent impacts and volcanic activity. The dark patches, called Maria, are vast plains of solidified lava. The lighter regions are covered with craters, evidence of billions of years of cosmic bombardment. The Moon also offers a tantalizing possibility for future exploration. Its poles contain water ice, which could support human bases. Imagine looking up at the Moon one day and knowing people are living there. That future isn't as far off as it might seem. Mars, the red planet and our future frontier. Now let's leave Earth behind and head to one of the most fascinating destinations in our solar system, Mars. The red planet. Its rusty color comes from iron oxide, basically, rust, covering its surface. But there's so much more to Mars than meets the eye. Mars is about half the size of Earth, and its thin atmosphere is mostly carbon dioxide, with only a trace of oxygen. Temperatures there are extreme, often dropping to -60 degrees Celsius at night. Yet, despite its harshness, Mars holds a special place in our imaginations. Why? Because it's the most likely candidate for humans to colonize in the near future. Billions of years ago, Mars was a very different world. Evidence suggests it had liquid water flowing across its surface, rivers, lakes, maybe even oceans. Imagine standing on ancient Mars, with a blue sky and water lapping at the shores. But over time, the planet lost its magnetic field, allowing the solar wind to strip away its atmosphere. The water either evaporated into space or froze beneath the surface. Today, missions like NASA's Perseverance rover and China's Tianwen-1 are exploring Mars, looking for signs of ancient life and testing technologies that could support human explorers. Imagine the first Mars colony, living in domes, growing food in Martian soil, and using 3D printed habitats made from Martian regolith. It's not science fiction anymore, it's science fact in the making. But why are we so focused on Mars? It's not just about exploration. It's about ensuring humanity's survival. As Carl Sagan famously said, all civilizations become either spacefaring or extinct. Mars could be our stepping stone to becoming a multiplanetary species. The gas giants, Jupiter and Saturn. Let's venture farther out into the solar system to meet the gas giants, starting with Jupiter and Saturn. These colossal planets are like the kings of the solar system, each unique and awe-inspiring. Jupiter, the largest planet, is a giant ball of hydrogen and helium. It's so massive that it could fit all the other planets inside it, and still have room to spare. But what really steals the show is the Great Red Spot, a storm larger than Earth that's been raging for over 300 years. Jupiter also has a magnetic field 20,000 times stronger than Earth's, creating dazzling auroras at its poles. And let's not forget Jupiter's moons. With at least 95 confirmed moons, it's like a mini solar system. One of the most intriguing is Europa, which has a subsurface ocean beneath its icy crust. If life exists elsewhere in our solar system, Europa is a strong contender. Now, on to Saturn, the jewel of the solar system. Its iconic rings are made of ice and rock, ranging in size from tiny grains to chunks the size of a house. These rings are thought to be the remnants of a shattered moon or comet. Saturn also boasts fascinating moons. Titan, its largest moon, has lakes and rivers of liquid methane and a thick atmosphere rich in organic compounds. Scientists believe it could harbor some form of alien life, even if it's wildly different from anything on Earth. Enceladus, another moon, has geysers that spew water vapor and organic materials, hinting at an underground ocean. Imagine what secrets these gas giants and their moons might hold. Uranus and Neptune, the ice giants. Next, we journey to the outer reaches of the solar system to meet Uranus and Neptune, the ice giants. They may not get as much attention as Jupiter and Saturn, but they're equally fascinating and mysterious. Uranus, often called the sideways planet, is unique because it rotates on its side. Its axis is tilted at a dramatic 98 degrees, likely due to a colossal collision in its past. This tilt gives Uranus the most extreme seasons in the solar system, with each pole spending 42 years in darkness and 42 years in sunlight. Uranus's atmosphere is rich in hydrogen, helium, and methane, the last of which gives the planet its pale blue-green color. But beneath that serene appearance lies a tempestuous interior. Uranus might have an ocean of superheated water and ammonia deep inside, a strange, exotic mix where diamonds could literally rain down. Yes, diamond rain. Now, let's move to Neptune, the farthest planet from the Sun. It's a deep blue world, thanks to the methane in its atmosphere, And it has the fastest winds in the solar system, reaching speeds of 2,100 kilometers per hour. Imagine winds so powerful they could shred anything in their path. Neptune also has a moon, Triton, that's truly special. Triton orbits Neptune in the opposite direction of the planet's rotation, suggesting it was captured from the Kuiper belt. Triton has geysers that erupt with nitrogen gas, and scientists believe it could have a subsurface ocean. The ice giants challenge our understanding of what's possible in planetary science, and there's still so much to learn. Beyond Neptune, the Kuiper belt and Pluto. As we move even farther out, we enter the Kuiper belt, a vast region filled with icy bodies, dwarf planets, and comets. It's like a treasure chest of the early solar system, holding clues to how our cosmic neighborhood formed. Pluto, once the ninth planet, is the most famous resident of the Kuiper belt. It's a small, icy world with a heart-shaped glacier made of nitrogen ice. Pluto's surface is a mix of mountains, plains, and craters, and it even has a thin atmosphere that freezes and collapses when it's farthest from the Sun. Pluto's largest moon, Charon, is almost half its size, making it more of a double dwarf planet system than a planet-moon duo. Together, Pluto and Charon form a cosmic dance, locked in a gravitational embrace. But the Kuiper belt is more than just Pluto. It's home to other dwarf planets like Eris, Haumea, and Makemake. Some of these objects are so far away that their orbits take hundreds of years to complete. And beyond the Kuiper belt lies the Oort cloud, a theoretical shell of icy objects that marks the edge of the Sun's influence. The Oort cloud is the birthplace of long-period comets, which can take thousands or even millions of years to orbit the Sun. These outer regions of the solar system are like the uncharted frontiers of an ancient map, mysterious, full of wonders, and waiting to be explored. Comets and asteroids, cosmic time capsules. Let's turn our attention to comets and asteroids, some of the solar system's smallest but most fascinating objects. These cosmic time capsules offer a glimpse into the ingredients that formed the planets billions of years ago. Asteroids are rocky bodies that orbit the Sun, mostly found in the asteroid belt between Mars and Jupiter. They range in size from tiny pebbles to Ceres, a dwarf planet about 940 kilometers in diameter. Some asteroids are rich in metals, making them potential targets for future space mining missions. Comets, on the other hand, are icy visitors from the outer reaches of the solar system. When a comet gets close to the Sun, its ice vaporizes, creating a glowing coma and a tail that can stretch millions of kilometers. These tails always point away from the Sun, pushed by the solar wind and radiation. But comets aren't just beautiful, they're also scientifically valuable. They're thought to contain organic compounds, the building blocks of life. Some scientists believe that comets may have brought water and these compounds to Earth, kickstarting life itself. Every time a spacecraft visits an asteroid or a comet, like the Rosetta mission to Comet 67P/Churyumov-Gerasimenko or NASA's OSIRIS-REx mission to asteroid Bennu, we learn more about these fascinating relics of the early solar system. They remind us that even the smallest objects can have the biggest stories to tell. The Sun, our life-giving star. Now let's focus on the heart of our solar system, the Sun. It's easy to take this blazing sphere for granted, but without it, life on Earth wouldn't exist. The Sun is a nearly perfect ball of hot plasma, and it accounts for 99.8% of the solar system's total mass. It's a middle-aged star, about 4.6 billion years old, and it's halfway through its life. The Sun's energy comes from nuclear fusion in its core, where temperatures soar to about 15 million degrees Celsius. Every second, it fuses around 600 million tons of hydrogen into helium, releasing an incredible amount of energy. This energy travels outward through the Sun's layers, eventually reaching us as sunlight after an 8-minute journey across 150 million kilometers. But the Sun isn't just a steady source of light and heat. It's an incredibly dynamic and violent place. Solar flares and coronal mass ejections can release enormous amounts of energy, sending charged particles hurtling toward Earth. These particles interact with our magnetic field, creating stunning auroras near the poles. However, a large solar storm could disrupt power grids and communications, something scientists are carefully monitoring. The Sun also has cycles of activity that last about 11 years. During the peak of this cycle, called the solar maximum, the Sun has more sunspots and flares. At its quietest, during the solar minimum, it's relatively calm. Despite its importance, the Sun won't last forever. In about 5 billion years, it will run out of hydrogen in its core and expand into a red giant, swallowing the inner planets. Eventually, it will shed its outer layers, leaving behind a white dwarf, a glowing ember of its former self. It's a sobering reminder that even stars have lifetimes. Dark matter and dark energy, the invisible universe. Now, let's talk about the parts of the universe we can't see, dark matter and dark energy. Together, they make up about 95% of the universe. That means everything we can see, stars, planets, galaxies, is just a tiny fraction of the cosmic puzzle. Dark matter doesn't emit, absorb, or reflect light, making it invisible to telescopes. We only know it exists because of its gravitational effects. For instance, galaxies spin faster than they should based on the visible matter alone. Something unseen, dark matter, must be holding them together. Scientists believe it could be made of exotic particles yet to be discovered. Dark energy is even more mysterious. It's the force driving the accelerated expansion of the universe. Imagine throwing a ball in the air and expecting it to slow down and fall back, but instead, it speeds up and shoots into space. That's what the universe is doing, and dark energy is the reason. The discovery of dark energy in 1998 was a game changer. It showed that the universe's fate isn't just a slow cooling and fading. Instead, it might keep expanding forever, with galaxies moving so far apart that the night sky will one day be almost empty. Understanding dark matter and dark energy is one of the biggest challenges in physics. They remind us that for all we've learned, the universe still holds its deepest secrets tightly. The multiverse, infinite possibilities. What if our universe isn't the only one? What if it's just one of countless universes in a vast multiverse? This idea, though speculative, has captured the imagination of scientists and storytellers alike. One version of the multiverse theory comes from quantum mechanics. It suggests that every time a quantum event occurs, the universe splits into different branches, each representing a different outcome. This is called the many worlds interpretation. Another idea comes from cosmic inflation, the rapid expansion that occurred right after the Big Bang. Some theories suggest that inflation didn't stop everywhere at once. Instead, it created bubbles of space-time, each with its own laws of physics. Our universe is just one bubble in this cosmic foam. If the multiverse exists, it raises profound questions. Are there other versions of you, living slightly different lives? Are there universes where the laws of physics are completely alien? Could we ever travel between universes, or is the multiverse forever out of reach? While we can't prove the multiverse, at least not yet, it's a tantalizing concept that pushes the boundaries of our understanding. It forces us to think about the nature of reality and our place within it. Time, the fourth dimension. Now, let's unravel one of the most mysterious aspects of the universe, time. We experience it every day, but what is time, really? And why does it flow in one direction? These questions have puzzled philosophers and scientists for centuries. Time is often referred to as the fourth dimension, alongside the three spatial dimensions. Together, they form what we call space-time, a concept introduced by Einstein's theory of general relativity. Space-time isn't just a passive backdrop, it's a dynamic fabric that can bend, stretch, and warp due to gravity. Imagine a trampoline with a heavy ball in the center. The ball creates a dip in the fabric, and smaller objects roll toward it. This is how massive objects like stars and planets warp space-time, creating the force we perceive as gravity. And this warping also affects time. Near a massive object, time moves more slowly. This is called time dilation, and it's been confirmed by experiments, like observing the behavior of clocks on satellites. But why does time only move forward? This is tied to the concept of entropy, the measure of disorder in a system. The second law of thermodynamics states that entropy always increases, giving time its arrow. It's why we remember the past but not the future, and why we age rather than grow younger. Then there's the question of time travel. If time is a dimension, could we travel through it like we travel through space? In theory, yes. Wormholes, hypothetical tunnels through space-time, could connect different points in time and space. But practical time travel faces enormous scientific and technical challenges. Still, the idea captures our imagination and fuels countless stories about bending the rules of reality. Extraterrestrial life, are we alone? As we gaze at the stars, a question lingers: are we alone in the universe? With billions of galaxies, each containing billions of stars and potentially trillions of planets, the odds seem in favor of extraterrestrial life. But where is it? This paradox is what physicist Enrico Fermi pondered in 1950, and it's now known as the Fermi paradox. One possibility is that life is rare or even unique to Earth. For life as we know it to arise, a planet needs just the right conditions: liquid water, a stable climate, and a protective atmosphere. While we've found thousands of exoplanets, very few meet these criteria. Even so, the discovery of extremophiles, organisms that thrive in extreme environments on Earth, has expanded our understanding of where life might exist. What about intelligent life? It's possible that advanced civilizations are out there but too far away for us to detect. Or maybe they communicate in ways we don't understand. Projects like SETI, Search for Extraterrestrial Intelligence, are listening for signals, but so far, we've found nothing definitive. There's also the idea of the Great Filter, a stage in the evolution of life that's incredibly hard to pass. Maybe we've already passed it, or maybe it lies ahead, in challenges like nuclear war or environmental collapse. Either way, the search for extraterrestrial life isn't just about answering a question, it's about understanding ourselves and our place in the cosmos. And then there's the possibility that life is hiding in plain sight. Microbial life could exist on Mars, Europa, or Enceladus, and we simply haven't found it yet. Missions like Europa Clipper and Dragonfly aim to explore these possibilities, bringing us closer to solving one of humanity's greatest mysteries: the end of the universe. Let's now confront one of the most profound questions of all: how will the universe end? While we don't know for certain, scientists have proposed several scenarios based on our current understanding of physics. One possibility is the Big Freeze, also known as heat death. In this scenario, the universe continues to expand indefinitely. Over billions and trillions of years, stars will burn out, galaxies will drift apart, and black holes will evaporate. Eventually, the universe will become a cold, dark, and empty void where entropy reaches its maximum, and no organized structure remains. Another possibility is the Big Crunch. Here, the universe's expansion slows and eventually reverses, causing it to collapse back into a hot, dense state, essentially the opposite of the Big Bang. Some theories suggest this could trigger a new Big Bang, creating a cyclical universe of endless rebirths. Then there's the Big Rip, where dark energy causes the universe's expansion to accelerate so much that galaxies, stars, and even atoms are torn apart. It's a violent and dramatic end that would leave nothing but particles scattered across the cosmos. Finally, there's the concept of a quantum fluctuation restarting the universe, similar to the conditions of the Big Bang. This could happen after trillions of years, in what's sometimes called a vacuum decay. Each of these scenarios forces us to grapple with the fleeting nature of existence. Yet, even as we consider the end, it's a reminder of the incredible beauty and complexity of the universe we inhabit today, the mystery of existence. Why is there something rather than nothing? We've spent the past 23 hours exploring the universe, its wonders, mysteries, and the science that seeks to explain it. But now, let's ask the ultimate question: why does anything exist at all? Why is there something rather than nothing? This question takes us beyond physics and into the realms of philosophy, metaphysics, and even theology. Scientists might say that the laws of physics allowed the universe to arise spontaneously from a quantum vacuum. But why do the laws of physics exist? And why do they permit life and consciousness? One perspective is the anthropic principle, which suggests that the universe appears fine-tuned for life because, if it weren't, we wouldn't be here to observe it. This leads to the idea of the multiverse. Perhaps our universe is just one of many, and we happen to live in one where the conditions are right for life. Others look to religious or spiritual explanations, seeing the universe as the work of a creator or a manifestation of a deeper, cosmic purpose. Still, others argue that the question itself might be unanswerable, a mystery that lies beyond human comprehension. What's clear is that the quest to understand existence isn't just about finding answers, it's about the journey. It's about curiosity, wonder, and the relentless drive to explore. As Carl Sagan once said, we are a way for the cosmos to know itself. And so, as we come to the end of this journey through space and time, we are left with a profound truth: the universe is vast, beautiful, and mysterious. We're just a small part of it, but through our curiosity and imagination, we can grasp its wonders. Thank you for joining me on this incredible exploration. Until next time, keep looking up and marveling at the stars.